Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments, and we're in part 4 of an 11-part mini-series within that playlist called Hierarchical Designs. And here we're going to look at the distribution of the sums of squares and f-test for this two-stage hierarchical design. As a reminder, the model is y equals x star beta star plus epsilon. So it is a linear model. And then we partition it into the mu, or the grand mean, factor A and factor B. But as a reminder, B is nested within A. Now I'd encourage you to go back to parts 1, 2, and 3 for more detail of that. Epsilon is normally distributed, mean vector 0, covariance matrix sigma squared I. Now the distribution of the sums of squares, we're going to pass you off to a playlist that I have. It's called Quadratic Forms, and in there we derive the distribution of quadratic forms. And so we're going to use some theorems in that playlist. Now note, y is multivariate normally distributed, mean of x star beta star, variance covariance matrix sigma squared I. Now we're going to look at the distribution of sum of squares error divided by sigma squared, and then that is this. So the sums of squares is y transpose, so I missed that already, I minus my, and then the sigma squared we'll put under this matrix. Now in order for the theorem to work, this matrix times the variance of y has to be an idempotent matrix. So let's check that. So here is this matrix. Variance of y is sigma squared I. So the sigma squareds cancel, I goes away, and we're left with I minus m, which is the perpendicular projection matrix on the orthogonal complement space of column space of x star. So, and it is idempotent. The rank of this matrix times the variance of y, which this is this, so the rank is AB times n minus 1, and we proved that in an earlier video. So the theory tells us that the sum of squared error divided by sigma squared is a chi-square distribution with degrees of freedom, the rank of the quadratic matrix times the variance of y, which is AB times n minus 1, and has non-centrality parameter, the mean of y transpose times that matrix in the middle times the mean of y. But I minus m times x star by definition is 0. So the non-centrality parameter is 0, and we're left with the central chi-square distribution with AB times n minus 1 degrees of freedom. Now the sums of squares for alpha, or factor A, divided by sigma squared, the sums of squares can be written like this. And note that we have to show that this matrix times variance of y is idempotent, so we look at that. Variances cancel, or sigma squareds cancel, I kind of goes away, and we're left with m alpha minus j, which is an idempotent matrix. Now the rank of that matrix is A minus 1. So the theory, and if you look at my playlist called Quadratic Forms, I have several videos called Distribution of Quadratic Forms. So it tells us that this sums of squares is a chi-square distribution, has A minus 1 degrees of freedom, and has non-centrality parameter, the mean of y transpose, times that matrix, right here, times the mean of y, which is this. Now in part 3, we derive this non-centrality parameter, or at least most of it, and it ended up this, the degrees of freedom comes down, and then this in scalar form is this expression right here. And we're going to use this. Now notice when we conduct a test for no factor A effect, then this non-centrality parameter has to be 0. And so in order for this to be 0, each of these have to be 0. And on the next page, I'll try to illustrate what that means. Now, the sum of squares for factor B, remember, but it's nested within factor A, divided by sigma squared, is this. This was the quadratic form. We have to see if this matrix times the variance of y is idempotent. So that's this matrix times the variance of y. Sigma squareds cancel, I kind of goes away. We're left with m beta minus alpha, which is an idempotent matrix. It's a perpendicular projection matrix. The rank is AB minus A. So that says that this sum of the squares divided by sigma squared is a chi-squared distribution with degrees of freedom A times B minus 1, with this non-centrality parameter, which is the mean of y transpose times that matrix in the middle times the mean of y. And in part 3, we showed that this has a scalar form of this. And again, this makes perfect sense given the design that we're in. Now, to do an F test, so let's assume there's no factor A effect. And so if these were A, factor A, and then factor B were nested within A. So if we're testing that this effect is the same as this effect, which is the same as this effect, isn't that similar to the average effect here has to equal the average effect here, which has to equal the average effect here? And that's actually the null hypothesis that we're testing, that the alphas are equal and that the average effects here, here, and here are the same. They're constant. And that's what this null hypothesis represents. And if we look on the previous page at this non-centrality parameter, this is saying that the alphas are the same. And remember, this is the average beta within I, within a factor level. And it has to be constant. And that's for each I. And so that's what that's saying. Those groups of 3 have to be the same. And the same goes for here. If the alphas are the same, then this is 0. Or if the average effective beta is the same. Actually, I think that one, should be a bar. So going back here, this is the null hypothesis, and this is the alternative, that they're all equal, that something's not the same. The test statistic becomes the mean square for alpha divided by the mean square error. And under the null hypothesis, there's no non-centrality parameter. So it becomes a central, this is it's distributed as a chi-square, right? With this degrees of freedom and this non-centrality parameter. But under the null hypothesis, this goes to 0 and it becomes a central chi-squared. Now to show that the numerator and denominator are independent, we have to show that matrix in the middle multiplies to 0, and this does, right? These are all within the column space of X, and this projects onto the orthogonal complement of that design matrix. So by default, it has to be 0, which says the numerator and the denominator are independent. Now, no factor B effect, it can be this way. So in matrix form, it's saying that if we project, the column space of X, or beta, so X beta, beta, if we project it into the column space of beta, it's equal to if we project it in the column space of alpha. It's essentially saying that all those betas within a group are equal. And so in scalar form, it's this, right? It's for each I, the group of 3 is constant. And that's what this says. And for there to be a beta effect, one of those have to be different, you know. The test statistic is the mean square for beta divided by the mean square error. And this is the, it's distributed as a chi-squared, non-central chi-squared, with a b minus 1 degrees of freedom, and this the non-centrality parameter. Now under the null hypothesis, this goes to 0 and it becomes a central chi-squared, showing that these are independent, is showing that the multiplication of those the matrix in the middle of the quadratic form is 0, and it is because each of these you project into the column space of X star, you know, the design matrix. And this projects perpendicularly, so it has to be 0. It says those two are independent. Now the ANOVA table for this design, we have A and then B within A, the error and the total. And it's these quadratic forms. Now, as you look at this, it looks kind of crazy. You know, it's like, what, all this multiplication is really what it is? And it is. When we do the R software illustration of this, these 100% agree with what R produces. The degrees of freedom, mean squared column is the sum of squares divided by degrees of freedom. F test is the mean square for alpha divided by mean square error, and then the same way here. Alright, well that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks, bye.